Chapter 9 Study Guide, question number 25. I'm going to white out the bottom to give us some working space. It wants to know AI. So what we see as far as a rule, we see EU, a radius, perpendicular to chord AO. So there's the theorem that we've memorized. A radius perpendicular to a chord. If a radius is perpendicular to a chord, then it bisects the chord and the arc of the chord. If a radius is perpendicular to a chord, then it bisects the chord and the arc of the chord. Now, if I extract that right triangle, then this is 3 and this is 6, and that's a right angle. You may notice that these are in the ratio of 1 to 2. 3, 6 reduces to a half. That tells me, since I've memorized my 30, 60, 90 triangle ratios, if that's in the ratio of 1 to 2, then this is the short leg and this is the hypotenuse, and so this would be the long leg, which is the square root of 3 number. Okay? They're in the ratio of 1 to 2 to the square root of 3. And so just from that, I would know that the angles are 30, 60, 90. And the long leg is equal to the short leg times the square root of 3. So I can know that based on everything we've learned so far. AI is 3 square root 3. AO is double that, 6 square root 3, because if a radius is perpendicular to a chord, it bisects the chord and the arc of the chord. Angle AEU is that 60 degrees. Arc AO, central angle EAU is 60, therefore the arc it hits is 60. The radius was perpendicular to the chord, so it bisects the chord and the arc of the chord, so we got 60 and 60 is 120 for AO. And you may say, well, I didn't remember that ratio 1 to 2 being a 30, 60, 90. What if I don't remember that? How are we supposed to remember that? Well, first of all, remember it. Second of all, if you don't, there's other options. So let's look at the other options. Let's say it didn't hit you that, hey, that was in the ratio of 1 to 2, therefore it's 30, 60, 90. So we think, well, how else could we find AI? Well, if this is 3 and this is 6, then you could find AI using the Pythagorean theorem. C squared equal A squared plus B squared. So we take C, which is our 6 squared, is equal to the side we don't know. We'll call it A squared plus the other side B, which is 3 squared. So we're going to have 36 is equal to A squared plus 9. Undo addition by subtraction. We're going to have A squared is equal to 25. Undo the square with the square root. And so we would have A equal 5. I messed up. Sorry about that. 36 minus 9 is 27. How about that? So we get A squared is equal to 27. We're going to get rid of the square with the square root. The square root of 27, we have to break it down. Divided by 3 is 9. Divided by 3 is 3. Rewrite it as the product of its primes. Circle pairs for square root. Make a new radical. From each set, you bring out that number. What wasn't circled in a set goes back in. And so we get 3 square root 3. That's better, isn't it? And again, if this is 3 square root 3, then this is 3 square root 3, so the whole thing is double that 6 square root 3. And you may still say, well, I still don't know. I still didn't remember from the ratio of 3 to 6 to 3 square root 3. It just didn't pop out in my mind that it was 30, 60, 90 because those were in the ratio of 1 to 2 to the square root of 3. So if that didn't pop out and hit you, then how could you find an angle measure? Well, you would have to use a trigonometric ratio. So we could say, well, I'm looking for the angle at E. So I'm going to say angle E equal. And I'm going to look at the sides given and see how they're related to the angle that I chose. And the 3 is the leg adjacent. And the 6 is the hypotenuse. So we chose the angle E. We've got the side 3 and we've got the side 6. The 6 is the hypotenuse. The 3 is the leg adjacent. Leg adjacent hypotenuse is cosine, so we use the cosine function. And then we set up the fraction according to cosine. Cosine says you put leg adjacent 3 on top, hypotenuse 6 on bottom. So we've got our ratio. We're going to change that to a decimal by dividing. And so we get cosine angle E is equal to 0.5 as a decimal. I apologize, I'm having some technical difficulties here. And then we want to get rid of cosine. So we're going to do the inverse of cosine function, which is inverse cosine function. So we need to do inverse cosine of 0.5. We're going to go to the graphing calculator. Hit mode, make sure it's still on degrees. It is. We want inverse cosine 0.5. And we get 60 degrees. Remember, we still have it on float 4. 60 degrees. And so then if the angle is 60 degrees, then the arc, this is crazy, is 60 degrees. So this arc is 60 degrees. So from here to here is double that, 120 degrees. Okay? So we could have used the Pythagorean theorem. We could have used a trigonometric ratio. If we realized it was in the ratio of 1 to 2 and it's 30, 60, 90, then we obviously got there quicker. Okay? All right. Numbers 29 and 30. What we see here is equal chords. This chord has 1 mark. This chord has 1 mark. In equal circles or in congruent circles, in equal circles are in the same circle, or we could say in congruent circles are in the same circle. Equal chords have equal arcs. The arc of the first chord there is 100, therefore the arc of this chord is 100. So arc YZ is 100 degrees. Well, what about arc XY? Well, we know that a circle is 360 degrees. We've got a 100-degree arc, a 90-degree arc, a 100-degree arc. We add those up, we get 290 degrees. Subtract from 360 degrees, and we have 70 degrees left for arc XY. Any questions on that? Okay. Number 31 and 2. We have the distance from the center to this chord is 3. The distance from the center to this chord is 3. So chord AB and chord CB are equally distant from the center. In equal circles or in the same circle, chords that are equally distant from the center are equal chords. So chord CB is the same length as chord AB, and its arc measure, arc AB, is the same as arc CB. Now we know that a circle is 360 degrees. Everything but arc AB and arc CB is 160. So 360 minus 160 would give us the sum of arc AB and CB. Since they're the same, we could divide their sum by 2 and get the measure of each one. So arc AB is 100 degrees and arc CB is 100 degrees. So arc AB is 100 degrees. Angle CXB, CXB is from C to X to B. It intercepts this arc of 100. Its vertex is the center. If the vertex is the center, then the angle is equal to the arc. So angle CXB is 100 degrees. Any questions on 31 and 32? Okay. Number 33 through 35, we have, and this 249 is the page number, by the way. Sometimes when I have page numbers close to problems, people think that that's a part of the problem. It's not. That arc out there is not 249. That's page 249 that we're on. Okay. We know that if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. If a quadrilateral is inscribed in a circle, then opposite angles are supplementary. Supplementary are two angles whose measures have the sum of 180. So angle A plus angle B is equal to 180 degrees. Therefore, the measure of angle A, which is x, plus the measure of angle B, which is x plus, that's a little bit unclear on my transparency. I'm going to pause. That is 40 degrees. I was just double checking. X plus 40 is equal to 180 degrees. So if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. So angle A, which is x, plus angle B, which is x plus 40, equal 180. We're going to do anything we can to simplify. In the order, please excuse my dear Aunt Sally, looking for distributive property and combining like terms. Understood 1x plus understood 1x is 2x, plus 40 is equal to 180 degrees. We've done all we can do to simplify. The variable is not on both sides, so it's time to undo. We're going to undo addition first by subtraction. So we're going to get 2x is equal to 140 degrees. We're going to undo multiplication by division, and we get x is equal to 70 degrees. If we want to find angle A was x, and x is 70, so angle A is 70 degrees. If we want to find angle B was x plus 40, so angle B is 70 plus 40, so angle B is 110, degrees. Any questions on 25 through 35? If a radius is perpendicular to a chord, it bisects the chord in the arc of the chord. That's 25 to 28. 29 and 30. in equal circles or in the same circle, equal chords have equal arcs, and equal arcs have equal chords. Number 31 and 32, in equal circles or in the same circle, equal chords are equally distant from the center, or chords that are equally distant from the center are equal chords. Number 33 to 35, if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. So those are the rules that were involved in those pictures. That's the basic rule, and then we had all the other stuff we're supposed to remember to go with it. Okay? All right, 36 through 38, we're going to clear below, clear the deck. Okay? Now, we're talking about angles and arc measures. So we're going to think about the chart on Unit 9.3. Where's the vertex and what's the rule? So it says angle 1. We say, well, where's its vertex? On the circle. If the vertex is on the circle, then it's 1/2 of the arc that it hits. So angle 1 is half of 50, which is 25 degrees. Okay? Angle 2, we would say, well, where's its vertex? The vertex is outside. If the vertex is outside, what's the rule? If the vertex is outside, the rule is that the angle is 1/2 the difference in the intercepted arc. What's the intercepted arcs? Well, from here to here and here to here. I want to move this other so we can focus on that problem. So the big arc is 30 plus 60, which is 90. And the little arc is 20. I'm going to wide out so we can make sure. Yes. Or erase. So the vertex was outside. The angle is half the difference in the intercepted arc. So angle 2 is 1/2 of 90 minus 20, which is 70. Half of 70 is 35. So angle 2 is 35 degrees. Okay? Angle 3, we say, where's its vertex? The center. If the vertex is the center, what's the rule? It's equal to the intercepted arc, 60 degrees. Any questions on 36 through 38? Okay. Number 39, arc FG. Uh-oh, this time we don't say where's the vertex. We've got an arc. So we say, well, where's the angle that hits it? The angle that hits it, we've got two choices. We've got this one, which is inside but not the center, so it's half the sum. That looks a little complicated right now. Let's see if there's another one that hits it. That's the only one that hits it, isn't it? So we have to use that one, even though it looks a little complicated now. So the vertex is on the inside, but not the center. So it's equal to 1/2 the sum of the arcs. Angle equal 1/2 the sum of the arcs. Well, we're looking for one of the arcs. So what are we dealing with? We're dealing with two chords that intersect inside of a circle. If two chords intersect inside of a circle, then the angle formed is equal to 1/2 the sum and the 1/2 the sum of the intersected arcs. What arcs? The arcs that form those vertical angles. So FG is an arc formed by the intersection of two chords. The angle formed, you see the 40 degrees, is equal to half the sum of those two green arcs. And the green arcs were the arcs of 40 and its vertical angle. So the angle, 40 degrees, is equal to 1/2 the sum of the arcs that's intercepted by it and its vertical angle. The one arc is what we're looking for, arc FG, and the other arc is 38 degrees. Now we're going to have to algebraically solve for the 40. Let's go ahead and distribute. You could multiply by 2 to both sides. Let's just do that. Because we learned if we don't like fractions, we just multiply by the reciprocal and get rid of it. And so we're going to have 80 is equal to arc FG plus 38. We're going to undo addition by subtraction. And so we get arc FG is equal to 42 degrees. That one was a little bit harder because we were looking for the arc. If the vertex is inside but not the center, then the angle is half the sum of the intersected arcs. We're dealing with an angle formed by two chords that intersect inside of a circle. Okay? Arc EF. Well, we're going to have to clean this out so we can kind of see what we're dealing with. We just learned that arc FG is 42. We're going to put that in the picture. We may need that. So we just learned that arc FG is 42 degrees. We're going to stick that in there in case we need it. Now it wants arc EF. Well, arc EF is not hit by an angle. There's not an angle. See, watch this. That hits the little thing EF. You see? Or if we went from this side, it's kind of dead ends. So it kind of looks like we're in a mess, right? But maybe we can do a little finagling. What's something that does hit a part of it at least? Well, that hits a part of it. Where's its vertex? On the circle. If the vertex is on the circle, then the angle is equal to 1/2 the arc. Well, we know the angle is 36. So the angle 36 is equal to 1/2 the arc. We don't know the arc. But the arc is the sum of those two pieces, right? That's a plus sign. So we could say that that angle whose vertex is on the circle is half of the arc that it hits. So it's half of the arc that it hits, and the arc that it hits is EF plus 42 added together. Well, that gives us an equation that we can solve with, and so we're going to do the same kind of thing. We're going to get rid of that half by multiplying by 2. We'll multiply by 2, and we'll get 72 is equal to arc EF plus 42. Undo addition by subtraction. We get arc EF is equal to 30 degrees. 30 degrees. Now, let's make that make sense better, just in case it didn't make real good sense to you. This is 42 degrees, and my board is kicking things out on me there. And we found out that this was 30 degrees. This angle right here has a vertex on the circle. The arc that it hits is supposed to be twice the angle 36. Twice 36 is 72 degrees. 30 plus 42 is 72. So that worked out. You can see all the algebra at the bottom of the page. You can see the basic mathematical logic at the top. Let's do the basic mathematical logic one more time without the algebra. That angle 36 has to be half of the arc that it hits. So the arc is double the angle. Double 36 is 72. We already knew part of that 72. FG is 42. So we can find the other part of the 42 by subtracting. And we did it without the algebra, although it's kind of nice if you know how to set up algebraic equations, okay? When we go to arc HI is here. It comes from an angle whose vertex is the center. If the vertex is the center, then the angle is equal to the arc, which means the arc is equal to the angle. And so arc HI is 45 degrees. Any questions on that? Okay. We're quoting lots of rules here. There's lots of memory work in geometry, as you can see. AC. AC is a tangent to the circle from a point outside. Well, so is this 8. This is the snow cone effect theorem from a few chapters back, right? Tangents to a circle from a point outside are equal. Tangents to a circle from a point outside are equal. Actually, it hadn't been a few chapters back. It's just I've recorded this entire book at nights and weekends and whenever I could in about a 3 to 4 week period of time. So when you teach an entire course in 3 or 4 weeks and you're still teaching school and preaching, it's quite a it's all kind of running together just a bit. But anyway, I did the teacher's edition in 3 weeks, and then I'm doing the whole video in 3 to 4 weeks, and I'm still teaching and everything. So I've been working day and night for a while. Anyway, so when I said this is we did this a few chapters back, it's just kind of a little bit of a blur. But anyway, so tangents to a circle from a point outside are equal. You didn't need all that information. I'm sorry. I call it the snow cone effect. That's like the blue's like a snow cone cup, right? All right. AB. AB. AB is the secant to the circle from a point outside, and 8's a tangent. So we have a secant and a tangent drawn to a circle from a point outside a circle. If a secant and a tangent are drawn to a circle from a point outside a circle, then the square of the tangent is equal to the product of the secant and its external segment. So the tangent 8 squared is equal to the whole secant, which we don't know that outside piece. We don't know this piece from here to here. But we could call that whole thing x, right? ABX. That's the whole secant times its outside piece or times the external segment 4. So if a secant and a tangent are drawn to a circle from a point outside the circle, then the square of the tangent, 8 squared, is equal to the product of the secant, x, and its external segment, 4. We're going to do the exponent. We're going to get 64 equal 4x. X times 4 is 4x. Undo multiplication by division, and we get x is equal to 16. So AB is 16. Any questions on 36 through 42? So, summarizing the little chart on Unit 9.3, if the vertex is the center, the angle is equal to the arc. If the vertex is on the circle, then the angle is half the arc. If the vertex is inside but not the center, then the angle is half the sum of the intercepted arcs. If the angle is on the outside, then the angle is equal to 1/2 the difference in the intercepted arcs. Tangents to a circle from a point outside are equal. If a secant and a tangent are drawn to a circle from a point outside a circle, then the square of the tangent is equal to the product of the secant and its external segment. In other words, tangent square equal whole secant times outside piece. So that's all the rules that were involved in 36 to 43. 44 through 47. Now, I'm going to scoot that up just a little. XE. XE is a piece of this chord. There's a theorem that says if two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. So 4 over x. Let me try that again. Having fun there, isn't it? 4 over x is equal to, we don't know, over 2. Well, we can't solve that because there's two unknowns. We know that the product of the segments of one chord is equal to the product of the segments of the other. Oh, that 14 is that other. That question mark's 14. There we go. Covered too much stuff up. Okay. If two chords intersect inside of a circle, I'm starting over here. I'm seeing crooked. I'm not sure what I'm doing. Let's start again and I'll do this correctly. If two chords intersect inside of a circle, then the product of the segments of one chord, 2 and 14, is equal to the product of the segments of the other chord or next. The product of the segments of one chord, piece times piece of the first one, is equal to the product of the segments of the other chord, piece times piece of the second one. There we go. Man, I had two whole different things going on. What I was saying and what I was doing on paper weren't even matching. I know that was weird. Okay. This is correct. If two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. In other words, piece times piece of the first is equal to piece times piece of the second. We're going to go ahead and do this multiplication and get 28 equal 4x. We can undo multiplication by division, and we're going to get x is equal to 7. So xe is equal to 7. Now, I realize I just called xex, but that's okay. We still got xe. Now, the triangles are similar by what? Well, there's only one thing we can say they're similar by now. And I'm going to put these numbers back in. We found out that xe was 7, so we're going to put a 7 there. All we know as far as angles is concerned is that our vertical angles are equal. There's three ways to prove two triangles are similar: side, 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 side angle, side, and angle, angle. Angle, angle, you would have to know all of the angles of one equal all of the angles of another, and we only know one pair of angles, so that's out. For side, 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 you would have to know that small over small equal medium over medium equal large over large. The sides are in proportion. We don't know all three sides, so we can't do that. To try side angle side, we need an angle of one is equal to an angle of another, and we have that. That's those vertical angles that were equal. But then we need to prove that the sides that form those angles are proportional, which means small over small has to be equal to large over large. So we're going to put small of this triangle 2 over small of this one 4. See, these are the sides that make those vertical angles. So small of the one on the little triangle goes with small of the one on the big triangle. Large of the one on the small triangle goes with large of the one on the big triangle. We're looking at the sides that formed those vertical angles. We put small over small and large over large and reduce. They come out equal, therefore they're proportional. So an angle of one triangle is equal to an angle of another. The sides that form those angles are proportional. Therefore, they are similar by side angle side similarity. They are similar by side angle side similarity. There you go. We need to name the similarity. The most obvious is the vertical angles. So X was last, so this X is last because they were vertical. We want to do the most obvious first. After that, what we have to do is we have to look opposite the small and look at opposite the large and the large. The small of this one was the 2. Opposite it is E. The small of this one was the 4. Opposite it is B. So B goes with E. And B was in the middle. So E goes in the middle. We've got EX. The only thing left is F. So F goes there. So we named the similarity. Any questions on number 44 and 45? Okay. Now, these triangles are twisted and spun around. You can't just go throwing numbers down here. When you name the similarity, we had to be very specific in getting our vertical angles equal and then looking opposite the smalls to get the angles that went together and looking opposite the larges to get the angles that went together. Okay? Or once we knew 2 out of the 3 letters, the third one was just there. All right, let's look at 46 to 47. We want AB. AB is secant. We have a secant drawn to a circle from a point outside. We have a second secant drawn to a circle from a point outside. If 2 secants are drawn to a circle from a point outside the circle, then the product of one secant and its external segment is equal to the product of the other secant and its external segment. I'm going to make this one red just so they're color-coded. So this whole secant in red, which we don't know, it's AB, times its outside piece or external segment 4 is equal to the other whole secant which we would have to add the 7 and 5 to know how much the whole thing was, 12, times its outside piece, 5. We're going to multiply, and so we're going to have 4AB is equal to 60. Undo multiplication by division, and we get AB is equal to 15. If two secants intersect a circle, now it says the triangles are similar by what? Well, we know that this whole thing is 12, and we just figured out that all of AB is 15. And so how could we prove that they're similar? Well, we can prove they're similar by either side, 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 angle, side, or angle, angle. Do we know any angles? Well, all we know that is that angle B of the little triangle here is the exact same angle as angle B of the whole big triangle. See the little blue triangle and the whole big green triangle? Angle B is the same angle. So we've got an angle is equal to an angle, but we've only got one angle. We don't know all three sides, so our only choice is side, angle, side. Now to prove it by side, angle, side, we need an angle of one is equal to an angle of another. That would be the B's. And the sides that form those angles are in proportion. So we're going to put small over small and large over large. Now in the blue triangle, we've got 4 and 5 as the sides of angle B. So we're going to put small 4, large 5 over. When we go to the whole big green triangle, let me just color code this in blue. The little blue triangle, the sides of angle B are small 4, large 5. The whole big green triangle, the sides of B are 12 and 15. Small 12, large 15, small 12, large 15. We have an angle of one triangle equal an angle of another. The sides that form those angles both reduce to a third. They are in proportion. So we can say that these triangles are similar by side angle side similarity. We want to name the similarity. The most obvious is that B is equal to itself B. That's that common angle B. Well, then how do we get the other? Well, we've got to think about what was opposite the smalls and what was opposite the larges. The smalls were 4 and 12. And so opposite the 4, that's this side, is angle E. Opposite the 12 in the big triangle, that's this side, is angle A. So angle E of the little one is equal to angle A of the big